Okay. So hello. Thank you for I was going to say coming to my talk, but you're not physically here. But thanks for watching my talk. My name is Andrew Sutton. Today I'm talking about reflection or compile time introspection of C++. Okay. So this talk is about language features for static reflection. I'm not. This is going to be bad. Okay. Apparently, PowerPoint is deciding to forward all of my slides for 2 seconds. Great. Yay, technology. Okay, so this talk about language features for C++, specifically for static reflection. I'm not, this is not a library or some emulation library. This is actual language supported reflection. So there are actual proposals for this. P1240 is the main proposal. P2237 is kind of like a big picture paper that describes a bunch of related features to reflection. And P2320 is kind of the latest paper that we've written for this particular feature. And it's also the syntax that's going to show up in this presentation. There are actual collaborators for this paper. It's not just me working on it. Primary collaborators are David van de Voorde from EDG, Wyatt Childers from Log3, which is my company, and Faisal Vali, who is a doctor, as it turns out. This is also not very speculative. There's an actual real implementation. You can go download this here. I'll mention more about that in a second. So this talk was initially planned to be, given last year, and it was supposed to be an updated version of a talk that I gave in CPPCon in 2019. But then this pandemic thing happened, and we couldn't do that. And then a year passed, and the language features and the compiler and everything has developed significantly since then. So I basically, looking at my slides from CPPCon, decided that I had to completely rewrite the talk from the ground up. So this is no longer a repeat talk. Okay, so as mentioned, there is an implementation. It's again on GitHub, log3 meta. The branch you would want to check out if you're going to try to build this and compile it is paper/p2320. It has most of the syntax described in that paper. We're still trying to hammer out some details of certain things. There are build instructions on the wiki for that repo, and the compiler is also available on Compiler Explorer. Thank you, Matt, for helping get that up, Matt and colleagues. If you go to cppx.godbolt.com, you can find this. Use the P2320 trunk version of the compiler to experiment, and it should just work. Hopefully, it just works. There are also a number of examples in this paper. These are in this repo that's also online called log3 struct algo, which is short for structural algorithms. It's kind of a mess right now because I was just using it as a testing ground for things that I thought would work. There are some reasonably well-developed examples, and there are some that are less well-developed, and there are some that just don't compile, and there are probably some that crash the compiler. So, don't assume everything there is pristine. You can, if you download the compiler, you can download this and build the examples. On Linux, this turns out to be fairly straightforward. On Mac, you also need a version of GCC that doesn't usually ship with Mac. Trunk is pretty good. I think GCC 10 works. So you basically need concepts and ranges. Unfortunately, Clang, which is what we're building on top of, libc++, their standard library doesn't have ranges yet, so none of the examples work. Or you could just give up and play with Godbolt or a Compiler Explorer. And I have no idea how to build this on Windows. I apologize. It's just not a system I build for very often. All right, so I want to start by talking about what is static reflection, just so we have some kind of framing for this discussion, because the idea of reflection can be fairly broad, and I'd like to kind of narrow down the scope of the features that we're actually going to talk about. So I'm going to take two examples, or two definitions here. One is from a paper on behavioral reflection from 1996. And the other is, of course, from Wikipedia, which is the ultimate source of knowledge in the universe. So why not? All right. So the authors of this paper on behavioral reflection say that reflection is the integral ability for a program to observe, and I can't see through Windows, to observe or change its own code as well as all aspects of its programming language, including syntax, semantics, and implementation, even at runtime. And then, of course, Wikipedia says that broadly, briefly, metaprograms have the ability to treat other programs as their data. So we're going to kind of craft these definitions, or at least consider various parts of them, and sort of narrow this down to figure out what it is we want to talk about for static reflection. So the first thing I want to do is just combine these together. We're not talking about reflection in the context of arbitrary programs. We can just say that we're going to talk about metaprograms. So reflection is the integral ability for a metaprogram to observe or change its own code, et cetera, et cetera. So second, let's just go ahead and strike even at runtime. The title of the talk should convince you that I'm not particularly interested in runtime reflection right now. So we can just go ahead and reduce this to static reflection is the integral ability of a metaprogram to do a bunch of stuff at compile time. So we don't have to think about runtime. We can also just go ahead and strike this. It turns out there are some interesting good reasons to do that. Syntax, semantics, and implementations change. So if you happen to write metaprograms that depend on the structure of your language, or the grammar of your language, or I don't know, the intricacies of, say, overload resolution, or even worse, the intricacies of what Clang or GCC happen to represent in version 8 or 9 or 10, if you depend on that, your metaprograms just aren't going to work. Well, they're not going to be portable. They're going to end up being fairly brittle. So we want to try to we should try to isolate or insulate metaprograms from as much change by the language and their implementations as possible. And with regards to changing these things, I find that to be kind of suspect. I don't really want language features that let me change sort of the fundamental essence of what C++ is. You know, a class should be a class, and if you have a library that changes that meaning, I don't think we're writing C++ anymore. So we're going to rebase our definition. So static reflection is the integral ability for metaprogram to observe or change its own code at compile time. This is a pretty concise definition, but let's consider the two different aspects of observing and changing. So observing code is pretty important. This is kind of like one of the fundamental pillars of same language metaprogramming, and I'm restricting this to same language, meaning that we're not writing external programs that read C++ and then generate code for us. We're writing programs in C++ in the same translation unit that operate on code that came before that, essentially. So we're effectively using source code as an input to metaprogram. And this is not really fundamentally new. Like, we do this all the time, right? Template metaprogramming with type traits is exactly this. We have type traits that let us inspect or observe some properties of classes or other properties of types. And the metaprogram, or the template metaprogram, the instantiation of that thing, is kind of what's guiding what's actually being executed. And to a certain extent, we also get the same idea with generic programming and concepts. Concepts give us a really powerful set of features for investigating properties of types, mainly like what operations work with these types. And then generic, like because they're generic, because we have template instantiation, that's kind of the metaprogram that executes to generate code. So what does it actually mean to change code? You know, I think this really depends on what you mean by change. There's sort of two ways to look at it. Does that mean that we should be able to reach out and actually modify existing code? And my answer to that is, please, no, we should not do that. I think that tends to be a bit, it tends to be a bit suspect. You know, it may also not even be technically possible. Like if I could do this, if I could modify existing definitions, could I write a metaprogram that reached out and say added a virtual function standard pair? I think that would be bad. It'd be particularly bad if there were other parts of the program that already depended on the fact that pair was not polymorphic. So modifying existing code has a lot of technical challenges, and there are lots of good reasons why we shouldn't embrace this particular aspect of change. But if we want to talk about generating code, I think that's good, right? So if by change its own code, what we mean is that we can add to the program, like we already do that with templates. I mean, template instantiation generates new definitions. It changes the translation unit in the sense that it's sort of appending to what we've written, right? Pack expansion kind of does the same thing, even though it's part of template instantiation right now, but we can use that to generate new types and expressions. We have this feature that was planned for C++ 20 called expansion statements, which I'll end up talking about in a bit. And those would generate new statements. But again, they're appending code to your program. They're not changing code that already exists. And if we really want to take a step backwards, we can talk about macros as being generative because they add new tokens to your translation unit as they're expanded. But they don't really fall into what we would like to have as a category or a definition for static reflection, because you can't write macros that actually evaluate properties of C++. Like you can't write a macro that knows that a type is trivially constructible or something like that. The reason is macros tends to be processed away, or macros tend to be expanded in a phase of translation that isn't that happens before syntactic and semantic evaluation or analysis. Okay, so even though generating code is kind of par for the course, like we write template metaprograms all the time, even without necessarily knowing it, there's actually a really big set of problems here, right? Like, what kind of code can we generate? Can we generate classes? Can we generate functions? Can we generate parameters, expressions, statements? Like, can we generate parts of statements? Can we generate parts of classes? How do we actually want to describe the code that we're going to generate? Should we just use raw strings? Should we use sequences of tokens? Or should we use something more structured and sort of partially semantically analyzed like templates? So these are kind of like all really big questions that you have to ask for code generation. And I don't want to talk about that today. There's a separate proposal that deals with this called source code injection. I think the paper number is P1760, although I can't remember off the top of my head. So we're going to limit ourselves to a very narrow definition of generation for static reflection. We already have templates, and those are really powerful, but we're going to add a little bit more functionality to generate information related to reflected entities, which we'll talk about in a bit. Okay, so here's our final definition. Static reflection is the integral ability for metaprogramming to observe its own code and, to a limited extent, generate new code at compile time. And that's the feature that we're talking about today. So how to observe code and how to generate, to a limited extent, new code at compile time. So what is reflection good for? I mean, let's just spend a bunch of time talking about what reflection is. It would be nice if we actually had some context for which it can be used, right? I think to understand where static reflection is helpful, we kind of have to step back and think about where we intend metaprogramming to be used in general. Like if we actually have a bigger picture of what metaprogramming should be for C++. So generally, we want to write less code, write less boilerplate. Like if we can just have facilities that sort of just work for our data types, that's great. Especially if I don't have to write any weird macros that sort of repetitively redeclare things, that's even better. We want to be able to do more in library. We don't want to write as many language extensions. So every time that we have to have some property of classes, like whether something is trivially constructible or default constructible, no except destructible or constructible, we kind of have to have these sort of recursive walks over class hierarchy. And those always end up being defined by the language and implemented with compiler intrinsics. If we can lift that out of the compiler and if we lift that out of the core language, then we don't have to have that dependency on the language changing. We can just sort of update our libraries. One of the other main reasons we like metaprogramming is that we can hypothetically eliminate single tool, or we can have single tool builds. We can kind of eliminate DSLs and meta compilers and like IDL compilers that generate code for us. It would be great if we can do this. But the set of features required to do that are significantly more than just static reflection. Like we need a much bigger facility for injecting source code, for example. And then the last two are kind of interesting because they're sort of, I don't know what the good word is, they're sort of orthogonal to like observing and injecting code. If we can incorporate external data or specifications into a program, and this would be like standard embed, if you guys remember that proposal, then we can generate code based on whatever data is added to the program or whatever specifications are imported into the program. Like imagine being able to generate classes by reading a database schema, for example. And the opposite side of that, as we parse code or as we analyze with our translation units, we might actually want to be able to generate things besides object files, external resources. So you could, like the opposite of reading, generating classes from a database schema would be to generate the database schema from your class definitions. And those are kind of orthogonal. They have interesting complexities. They're still metaprogramming related in that these things have to happen at compile time. And there is an aspect of code generation, and there is an aspect of observation. So this paper P2237, it tries to kind of capture that big picture. But where static reflection helps, it's a little bit more limited in what we can do with just static reflection. We can usually use this to write less boilerplate, which is fantastic, and we can use it to write features that appear. We can use it to not write language features or not to define things in terms of compiler experience, intrinsics. Maybe it can help a little bit with single tool builds. For example, like GCC uses an external tool that parses its own source code to help generate garbage collection routines. I think that static reflection can basically replace that tool with a couple of other features to help guide it. But for things like IDL compilers or like Qt's meta object compiler, we're not quite there with just this language feature. And then we're not talking right now about embedding data in programs or exporting data from programs. So we're not going to think about that too much. But hey, if we can actually satisfy the first two points, that's a pretty good start. That's still a powerful set of features. And so it turns out that like a lot of the problems that we end up trying to solve with reflection, they can kind of reduce to this sort of nice little class of algorithms, or at least I've noticed that a lot of the problems that I've thought about reduce to this nice little class of algorithms, which are basically recursive algorithms over class structure. So it's defining things like type traits that look at members of a class to see if it's trivially constructible or no-throw constructible. Requires a recursive walk over your class structure. Serialization is the same thing. If you want to serialize a class, you have to walk members of that class. Hashing does exactly the same thing that serialization does. If we'd had reflection earlier in the language, maybe we wouldn't have operator spaceship, because that can be a library feature. I think pretty sure that can be a library feature. And I mentioned GCC and garbage collection. We can probably provide some level of opt-in, non-aggressive garbage collection just as a library that sort of just works. And then dynamic reflection is exactly the same thing, except instead of having everything at compile time, we're taking observed data and projecting that into runtime. I actually talked about that in my new 2019 talk, but did not update that for this talk. So these are kind of the examples that I'm going to end up talking about, or like some of these examples I'm going to end up talking about. But I think that these are great examples for the kinds of problems that we can solve today with the static reflection features in P1240. Okay, so the rest of this talk is pretty much just code, examples of static reflection, with some asides to explain particular features, semantics, rationale, like language constraints, design constraints, and things like that. All right, so I'm actually going to start off with a toy problem rather than a real example, just because this gives me the opportunity to talk about certain properties of C++ and reflection. This is actually ended up being derived from an example that I ended up posting on Reddit last week. Not quite in the context of static reflection, but how const eval should work and why it should work this particular way. So this is a great little function that is completely useless as far as I can tell. If you instantiate this with a type and a number, it will generate a pointer with that many asterisks after it. So if I call make indirect with int and 42, I will get int followed by 42 pointers. Not particularly useful, but interesting. The fun part about this is like it's a template metaprogram. I know it's not using a class, so I'm bucking the trend a little bit here, but it's still a template metaprogram. And so whenever we instantiate this, what it means is that we have to instantiate, like if I call this make indirect with int and 42, I'm going to end up with 43 different instantiations of this function. And those never go away. They end up in your symbol table, especially because this is an external function. So it's doing something fairly simple, but there's an associated cost that we tend to overlook with templates and metaprogramming. But if we want to know if it works, we can actually use the metaprogramming library to help test this. right? So get a pointer, make indirect int in 42. So we would expect a bunch of int with a bunch of pointers, and then we just go ahead and print that out. And this is where reflection starts being used here. So this thing here, the caret followed by pointer, that caret is the reflection operator. It's going to give me a handle to the variable or reflection of the variable. And then we can use that as input to metaprogramming, the meta library functions, which, oh, actually, sorry about that. So yes, this is a reflection operator. The reflection operator is an expression. It's just a normal expression. It's sort of a normal expression. It produces a compile time value, like a constant value that describes its operand, right? So if you write caret int, you can reflect a type name or type ID. If you write caret main, you can reflect an expression naming a function, assuming, of course, the function is in scope. You can reflect expressions. If you want to reflect something more complicated than like a literal, you can put it in parentheses. So you can actually reflect 2 plus 4, for example, the expression 2 plus 4. You can reflect on names of templates. You can reflect on names of namespaces. If you can write it in the program, you can reflect on it, except concepts, because we actually haven't talked about that language feature yet. So the idea was that the caret operator is intended to denote lifting or raising whatever its operand is to the meta level. So we're going to sort of lift this description out of the syntax into a level where we can start writing code against it, meaning that we're going to use it with library functions, essentially. So that operator, can I reflect on an overloaded operator set? The question is, can I reflect on an overloaded operator set? The answer is yes. You can also disambiguate it with a cast expression if you'd like. We're still trying to work out the semantics of reflecting overload sets, but I definitely want the answer to be yes. Okay, so the result of reflecting something is called a reflection. It's a value of type meta : info. This object is, or this value or type is it's sort of like an opaque scalar value. So it's kind of like int, but it's not kind of like int. You don't really know what it is, but under the hood, it's really a handle to an implementation's internal representation of whatever the operand is. If you've worked on compilers before, then you might recognize this as an AST pointer, an abstract syntax node pointer, that's been laundered into the translation system. In fact, that's actually how we implemented it in Clang. There are a couple of other ways to think about an implementation of this, but really we're just laundering AST pointers into the constant evaluation system. Now we do have a restriction on meta info values. They cannot leak to runtime because the things that they represent, the handles they refer to, those internal data structures, don't exist at runtime for the most part, right? Like we don't have runtime type information for ints or char or float or pointers. And we don't want to require that we actually add that to translation units. So for now, at least, if you're going to work with meta info objects, if you're going to work with reflections, they must exist at compile time. Okay, so we get a reflection of a local variable pointer. We can pass that to a meta function called type of. Type of is going to return a reflection of pointer's type, which in this case is whatever is deduced. That's going to be int with a bunch of pointers. And then we can take that reflection, the reflected type, pass that to another meta function called name of, which is going to generate a C string or string literal, whose value is the rendered name of the type. I should point out, since I'm looking at name of it a second, the names of library functions may change and the syntax of reflection may change. So just be aware that this talk may not survive the test of time, or at least some aspects of it anyways. So at the end of the day, what we actually end up doing is printing out this string literal int star, right? So all is well and good. We have a portable name generator. The reflection library, the meta library, is an extensive collection of functions. I think we were up to a couple hundred maybe in our last version of the paper. Type of and name of are shown here. Every meta function that we've defined so far is const eval, meaning that it's always executed. It's always executed where it's called. except when it's called inside of another const eval function. The idea here is that whenever you pass anything through a reflection or a meta function, you're always going to get a constant back. So we're trying to prevent these meta info objects or results related to meta info objects from leaking back into normal runtime code. Right? And so the reason that we can actually use meta, like name of, for example, in normal code, is it because we require the execution to happen right there where it appears, and we're not actually deferring that to a runtime call, for example. So, okay, so that's my toy little problem, but I'm going to adapt it for reflection, just because I don't like the fact that we end up generating 43 specializations of that function. So this is going to be my new version of make indirect. It's still going to be a template, so there's still going to be an instantiation, but it uses reflection in a slightly novel way. Right? So the kind of the high level picture of this particular function is that we're going to reflect the template parameter t, the type t, to get a meta info object. We're going to hand that off to a meta function called make pointer, which is then going to construct the pointer type, get a reflection of the pointer type. I see there's a question, give me 1 second. In reflection of the meta pointer type. And then we're going to take that reflected type and splice it back into the program as if we'd written it exactly here. Like it's basically, we're going to replace the some of this notation with the type that we've generated. Let's see here. So I know there's a question. I'm gonna get through this little section and then I'll answer that question if that's okay. So hopefully it is. Right. Okay, so just an anatomy of this particular function here. We were reflecting on the type t, so we're going to get a meta info or reflection of that particular type. Reflection doesn't actually happen at compile. Sorry, it doesn't happen. It doesn't apply to dependent names. So we're not reflecting the template parameter t. We're actually going to end up reflecting whatever gets substituted for t, anyways. Which in examples before would be int, for example. It just turns out that there's really no interesting properties of a template parameter other than like its name might be t. So we basically just made reflection live outside of templates. It just works like normal expressions. Now this make pointer is a meta function. It takes reflection as an argument. It must be const eval. It has to happen at compile time. And more importantly, it has to be computed at this particular point in the program. So it's just going to return a reflection of that computed type. Now that meta function is actually kind of amazingly simple to write. It's this. It looks like any normal function, except that it takes except that it's const eval and operates on this meta info object. But it's just got a normal for loop in it. It has assignments. It calls other functions that probably also have to be const eval functions, and it returns the value. What I think is particularly really nice about this function is, well, one, it's not a template. I don't have to think about templatey things. But two, we're actually using this type variable as a real type variable. We can actually program with types just like we can with values at this point using reflection. Okay, so the thing returned by that function, just computed by a simple loop, falls back into this thing with these weird little brackets. These brackets are called a splice. It is the opposite of reflection. So if you think about reflection as lifting things into this sort of metaprogramming environment, metaprogramming part of the language, which is really just constant expression evaluation. I shouldn't say it's a different part of the language. Then splicing a reflection will give you back syntax, essentially. Like it gives you back a reference to the thing that you've computed, or the reflection that you've computed. So this is our very limited form of code generation. If you have a reflection of something, you can always splice a reference to that thing back into your program. And that's the only generative feature that we've actually added to the program at this point. Let's see here. You know what? I guess I will answer this question right now because it's kind of easy to answer. So rather than storing names with const eval, can we store them with const init? I don't think so. I think that const init does something a little bit different. Const eval applies to so const eval applies to functions for the most part. Just saying you're going to evaluate a function where it appears in the program. Const init is, as far as I remember, as far as I know, just guaranteeing that the initialization of a global variable, for example, is done using constant initialization. If you use a constexpr function in a constant variable, const eval function in a constant variable, they kind of cancel each other out. It's just a constant expression. But they serve different purposes and don't really overlap. Okay, so splices, back to this talk here. Splices lets you insert references to reflections back into your program. Okay. And technically, the entire thing is called a type splice. It turns out that splices end up being a bit like dependent names, so that we have these rules about where you have to add keywords to tell the parser like what they are. They work basically exactly the same way that dependent names inside of templates work. Right. So the splice operator, there's a bunch of different variations of it. If you don't have anything in front of it, like without qualification, a splice by itself is an expression, considered to be an expression. We also allow splices to appear after a dot or an arrow, which is basically a spliced member access expression, which you're going to see a fair amount of in this talk, actually, or at least some examples of that. If you put the word template in front of it, you're effectively splicing a template name as part of a template ID list, or a template ID, like vector event. If you put type name in front of it, you're splicing the type. You can use splices as part of nested name specifiers, as the front of a nested name specifier. And again, you can put template there also. So basically, you can splice any part of the grammar that you can reflect. That's kind of the rule. And the specific rules for adding keywords are essentially the same as where you would require them inside of templates. And the reason for that is that inside of templates, splices are in fact dependent expressions, because you don't necessarily know what the reflection value is that you're going to splice in the program. So we need to give the compiler a hint to figure that out. Okay. So the notation for splicing is not an accident. It's kind of my idea. The goal is to really represent kind of a gap in the program. Like, here is a space in the program that you need to fill in by whatever refl is, whatever this expression is going to be. So it's kind of like literally the way that I think about it is you're sort of programming like a fill in the blank type programming model here. Like, I need a type, I have a reflection, go get that reflection and put that value in this particular place. Okay. Splicing, and like I mentioned that splicing is the inverse of reflection. There's actually an equation that governs this, which is that if you splice the reflection of a thing, it should be almost exactly equivalent to writing that thing directly into the program. There are two exceptions to that. And actually the second one isn't even really an exception. But the one exception that we do have is that access checking is not performed on splices. So if you've ever gotten a reflection for a private data member, for example, you can splice that into a program and it's going to work. And the reason we have that requirement, or that we allow that, is that we actually can't write any of the more interesting kinds of applications that we'd want with static reflection if we don't have access to private data members. So yes, there's a gigantic hole in the access checking model now, but without this, we would be kind of limited in what we can actually do with this functionality or these features. The other kind of exception that we'd have here is that the thing that you're splicing in the program, it just can't refer to local variables that haven't been declared in that context, which, I mean, if you think about it, you can't refer to variables that aren't in scope. So this is not really an exception. This is just, it just falls out of the way that we actually write C++. And so, yeah, so this is the entire function, the make indirect and reflective indirection generator. If you use it, if you call this function, you will get a specialization, but it will just be one specialization. For each pair of T and N, you won't get 43 of those. Let's see, so the question is, can you, through this access mechanism, tell the access of thing? Yes. There are meta library functions that let you determine if something is public or private or protected. So that's part of our gigantic meta library. If there's a property that you might be able to query, there's a good chance there's a function in the library that lets you query that. Okay, so on to real examples. Although stringifying enums has sometimes been referred to as not a real example. All right, so this is the all too common request. I have a simple enum. It's got some enumerators, green, yellow, and red for the color of a light. And I just want to print, the string value of that particular enumerator. Like, how hard should this be, right? I keep seeing libraries or emulation libraries for reflection where you keep having to declare parallel structures that actually encode these reflections. One of our goals was to make sure that you would never actually have to do that again. So I think the next slide is the definition of that. Oh, good, it is. So this is how easy it is. Like, this is the entirety of that program. There's a couple of things that we should probably talk about in this definition. So let's see. This is an expansion statement. This turns out to not work on normal for loops. And expansion statements were proposed for C++20, almost made it into C++20, but it was kind of late enough in the game that it got pulled, and should be in C++23 if I ever find the time to bring that back to core. These things are fantastic and are kind of the workhorse of static reflection. They'll show up in a bunch of different examples. So expansion statements, more specifically, the idea is that we're going to instantiate the loop body of every element in the range. So it kind of looks like a range-based for loop, except that the range is a little different. It can be anything that you can like initialize a structured binding with. So it can be a tuple, it can be an array, it can be a class, whatever the class rules are for structured bindings. And it can also be a range, as in the concept range, with constexpr begin and end. So as long as we can find constant bounds for this range, we can actually start destructuring, or expanding over that. And then what happens is that we effectively, for the loop variable, x in this case, we're going to initialize x with whatever the value of each element is, and then instantiate the body with x in mind, right? So in this case, x is declared as a constant expression, which means that we can actually use it in template arguments, which is fantastic. So the code above basically ends up becoming this. If you print constant x for each x in integers of 5, you get print constant 0, 1, 2, 3, and 4, with x being supplied as a template argument in each case, which is exceptionally powerful. All right, so back to our little implementation. So we have an expansion statement that runs over the members of the reflection of T. So as we instantiate this, the reflection of T is going to become the reflection of, was it light color? I think it was light color. Yes, light color, sorry. Becomes a reflection of light color. This members of meta function will give me back a constexpr range. I think this might actually end up being a constexpr vector as the library evolves. And we are going to initialize each such element of that range is going to be initialized to a constexpr reflection E, so that every value of E is going to be the reflection of an enumerator inside of the enumeration, if that makes sense. Basically, we're going to have E, that the first E is going to be green, the second E is going to be yellow, and the third E is going to be a reflection of red. And then in the body of this expansion statement, we're just going to compare each reflection of E to its value. Sorry, we're going to splice the value of the enumerator into the comparison. So we're generating code that would look like if green equals value, if yellow equals value, if red equals value. And then if that turns out to be true, we'll just return the synthesized name of the enumerator. So the code that we end up generating actually looks like this. If this would be a specialization for calling print or toString with light color. In fact, it looks almost exactly like this. So if green is equal to value, return green. If yellow is equal to value, return yellow. If red is equal to value, return red. Now the downside of this particular implementation is that if you put this in a loop to print out all of your enumerator names, it turns out to be unfortunately quadratic in the number of enumerators. So we would like to be able to do that better. And we were kind of thinking about ways to, the slide is not helpful, thinking about ways to do that. Next slide. And we kind of came up with this idea, which was to have a switch statement, well, to write the expansion statement inside of as the body of a switch statement, and so that you could expand each case label for each particular thing. So Richard's question, is there a template switch? This would be close to a template switch, except that it is not, and it doesn't work. Because unfortunately, we have this weird language rule that we're going to jump over, like that switch jumps over the initialization of constant expressions, which maybe it shouldn't. So like, there's probably a way to rewrite the language for this so that it lifts those each declaration resulting from the expansion statement out. It's tricky. So we're still kind of trying to figure out ways to make this more elegant. But this particular one seems like it would be a good approach. I think the language rules for making it happen would be fairly tricky, though, unfortunately. I think I gave a talk last year where I was using more advanced generative facilities, the source code injection stuff, to actually build a static hash table and automatically initialize that with pairs of names and values. So there are probably ways to make this faster. Let's see. So the question is, can you put the splice into a standard initializer list? And the answer is yes. You can splice into an initializer list. Okay. And I see the question about reflecting overload sets is still on the Q&A sign. I did answer that, and the answer was yes. You can reflect an overload set, although we're still trying to work out the semantics of it. Okay, so this is the main example for this talk. I figured we go from like toy problems to maybe possibly toy problems to like the hardest problem to solve, which is serialization. You know, if I'm writing code and I have, like if I'm writing a game, which I'm not, if I were a game designer, I am not. I might have a game class that looks like this, and it's got a player's name, maybe some health, maybe some magic, and then I should just be able to declare this little writer and run this to CO, right? Like this would be fantastic. So the question is, how much code do I actually need to add to my code base to make this happen, to make this work? And hopefully the answer is as little as possible, right? So just to show you what these classes might look like, here's my canonical player class. It's got some private data members, some public accessors, maybe some modifiers somewhere else. Although if it was just this class by itself, it wouldn't be a very good game because you can't modify the player at all. Health and magic are pretty simple classes. I'm just going to cheat and make little structs that have called a ratio of max and current. So this is not a very particularly complicated set of objects here. All right. So my claim, my observation is that these classes are simple or basic data types. They're not complex data structures. They don't have any indirection in them. Maybe they do, but the examples here don't. But they're not really like nodes and graphs, which makes serialization kind of hard. They might have inheritance involved. So my hope, my claim, my desire is that serialization should just work with these things. Right? I don't want to write any additional code just to serialize this into a JSON. And the implication of that, of course, is that reflection must be able to work on private data members. It has to. Excuse me. If I don't want to write any code, then I have to be able to define facilities that actually operate on code that would typically be hidden from me. Right? So serialization basically comes in a bunch of levels or flavors with increasing difficulty as you go down. So just to kind of sketch out the algorithm and talk about what we can and what we can't do. So serializing single objects like strings and ints and bools is pretty straightforward. There's nothing particularly difficult about that. Sequences, pretty easy, just serialize the length perhaps in advance. Trees are the more interesting things, just because almost everything turns out to be a tree. And then lastly, the most difficult thing to serialize are graphs, because you kind of have some interesting dependencies. You basically have to have referential data structures, referential structures in your serialization to make this work. But serializing classes is really just an instance of serializing trees. Serialization just happens to be one of these recursive algorithms on class structure with extensions for dealing with things like extension with indirection, pointers and graphs. Right? So we can think of it as a recursive algorithm. We have base cases, right? Bools, we can serialize true or false, numbers like 42 and strings, blah. I mean, if we really wanted null, we can serialize null also, in JSON anyways. And then for ranges, and I do mean this in terms of concepts, we can serialize an array. If we have a map or an associative container, maybe we can serialize objects with key value pairs. Although that gets interesting if you have to serialize a map with non-textual keys. So that's probably not going to happen very cleanly, unless we have toString defined for everything. And then for class objects, so like just arbitrary objects like player, game, and player, health, and magic, and things like that, we'd want to just serialize objects for these things. Let's see here. I am going to defer that question until later. So this is a question about circle lang at a non-syntactic lang. That's kind of a big question to answer. Okay. So if we want to write serialization, we can do this as a facility. Let's see, we gotta have some requirements. We could provide sort of a non-extensible version, like just a canned serialization of things that we know about, fundamental types, primitive types, bools, ints, whatever, ranges, maps, maybe classes. But then we want to be able to handle pointers and graphs and like interesting classes that the user provides, like their own custom data structures. We want to be able to provide hooks that allow, if my game were more complex than 3 classes that had no pointers, then I would probably want to be able to customize serialization facility for those particular types. So we're going to try to design the facility in a way that can be extended for application-specific use. And the way that I'm going to do that is the sort of compile time version of polymorphism. This is a curiously defined, curiously recurring template. This class is intended to be derived from or inherited from, and the first template argument is always going to be the class that inherits from this. And the idea is that I have this function called derived that will give me a reference back to that derived object. So I can always effectively call down into the derived class from code written up here. It's an extremely powerful idiom for writing extensible code. And just for completeness, like this is the actual writer class from the example. It derives from basic writer. It provides its own template argument itself as a template argument, and then that's it. It doesn't actually add anything to this. So everything else happens, for this example, everything else happens inside of basic writer. All right. The main serialization interface to this facility, I'm just going to call it write, because that seems like a nice name for this function. And it's going to take a type, any type, and then it just calls derived, write value on the derived class. So write value is the real workhorse of this particular facility. The fact that we're calling it on the derived object means that whoever inherits from this class is going to have an opportunity to add to what it means to write a value, whether they're going to add overloads or just completely replace this function altogether. Okay, so this is my serialization of base cases. These are pretty straightforward. I have an overload for write value for bools. I have an overload for write value for arithmetic numbers. Oh, and I didn't mention this. I should probably mention this talk relies on concepts quite heavily. I've gotten to the point now that I don't write code without concepts. Which probably means I'm not writing production quality code because nobody's using C++20 in production yet. But concepts are amazing, and this talk is going to end up being about generic programming as much as it is about reflection, as it turns out. So arithmetic as a concept is basically any integral type or floating point type. We can just write out the value of those things. Character string is just a concept that I invented for the purpose of this slide. It's not even in my implementation on the struct algo repo. That would be, I realized I didn't write this generally enough. This would cover cases like every specialization of standard basic string for any character type, for any set of character traits, and also for string view. So it would cover all of those things. So these are kind of the primitives that we want. And then if we wanted to continue this pattern, we'd have like an overload for ranges, because we can serialize a range pretty easily. We might have an overload for associative containers. We might have an overload for basic data types, and I'm going to talk very specifically about basic data types in a bit. But I am using this concept of basic data type to refer to classes like player or health or what do you call it, or magic, sort of these classes that aren't necessarily characterized by other concepts. They're not integers, they're not floating point numbers, they're not ranges, they're not really containers. They're just sort of, data types that live in the application domain. Okay. So this would be ideal. Like, this would be fantastic if we could make this work, but it doesn't, unfortunately. And this is really my fairly long aside about generic programming in this case. Unfortunately, all of these overloads are ambiguous. Well, not all of them. Some of these overloads are ambiguous. So the relationship between strings and containers and ranges is reasonably well known, right? I'll just leave this up because it's more interesting to look at. Okay. An associative container is a range, right? It has a begin in it, like this unordered map, standard map, whatever. That is a range. Even going back to character string, we have overlap here too. Strings are also ranges. They have a begin and an end, right? So we know the relationship between these things really well. And if we only had these three overloads, then we wouldn't have to do anything else. Because if I instantiate with a character string, assuming it refines range, overload resolution will just kind of pick that up. Like we're basically ordering overloads based on their constraints, and we can actually choose the right things based on what we get. Same with associative container. Yeah, an unordered map would be a range, but it's more of an associative container, so we're going to pick that particular overload. The problem is with these basic data types is that it partitions the set of ranges. Like, everything else is a range, so we're just going to partition the set. Some ranges are going to end up looking like basic data types. Possibly some strings are going to end up looking like basic data types. I think it's unlikely that an associative container would look like one, but it's possible, right? So what happens is that if you try to call this function, this right value, with any type that satisfies both basic data type and range, for example, it's ambiguous. These concepts are entirely unrelated. They're not comparable, and so you end up with an ambiguous overload resolution. Now, I've run into this problem a couple times before, and my gut reaction is kind of like to take a step back and go, I think I've designed my concepts incorrectly, but it turns out you haven't. Do not try to redesign your concepts to solve this particular problem, because you're going to try to optimize your concept hierarchy for this instance of the problem, but it's not going to work for the next instance of the problem down the road. Like, your concepts are correct, they just overlap. We just need to figure out what problem we're trying to solve, and it's not a problem we can solve with refinement, with concept refinement. The problem we're actually trying to solve is specifying preference. We actually prefer how to choose these particular things. And our right value function, we can actually encode that really easily. And the basic logic of it would look like this. If it's an associative container, try to serialize that as an object. If it's not that, if it wasn't an associative container, but it was a string, we'll try serializing this as a string. Failing that, we'll fall back to a range. If it's in a range, then we'll do that thing. And lastly, we'll just assume that it's a basic data type and try to serialize it. Try to serialize it that way. Now what was it? Oh shoot, I got lost. Yeah, so fortunately we have really nice tools in C++ to express this quite directly. If constexpr is fantastic, it works really nicely with concepts. We can actually express our preference in resolving these overloads like this. So if constexpr T is an associative container, do this thing. If it's a string, do this thing. If it's a range, do this thing. Otherwise, we'll just try to write it as a class. Okay. But I think we can actually do a little bit better, right? Remember that containers, associative containers and strings are also ranges, right? So we can actually minimize this particular definition. We can make it a little bit more open and extensible. And we'll make it correct by actually just writing a requirement on top of this. So we only really need to look to see if it's a range. And if it is a range, we can delegate to a function called writeRange. And now this can actually have the overloads for character strings and associative containers. Now, what I like about this approach is that it moves us out of this kind of closed system where we have to fully specify the order in which we prefer things. back to a more open system. So if we wanted to add more versions of or more overloads of right range, we can do that without modifying any existing definition. As long as it is a range and it has these particular properties, we can just like add overload sets and let overload resolution pull those apart or pick our overloads for us. And it should do it correctly. And then, of course, you fall back to class in the other case. The reason this is also more extensible is that we're actually delegating these calls back to the derived class, meaning there's an opportunity for an application-specific deriver of the facility to sort of, what's what I'm looking for, intercept or to extend in application-specific ways the responsibilities of these particular functions. Okay, I think that's the end of my little diatribe on generic programming and preference. So on back to serialization. This is the right class function. It's surprisingly straightforward, surprisingly simple. Let's see here, what happens here. So just like it's a little bit like working with enums, except we're working with the data members of the class. So for example, in this case, we're just going to ask for all data members of the reflection T. I think I may have implemented this differently in my examples. Oh, anyways, so we reflect the class T, whatever class we're going to write, we're just going to grab all of its data members. This gives us a constexpr range so we can iterate over. Again, we have an expansion statement over that range of members, binding each such member to a constexpr reflection of members. So we're going to expand over a reflection of every member. And then let's see, we're going to serialize it so the name of the member is going to be the key. So if it was like m_name, m_health, and m_magic, that's going to be the name of the key for the object that we're serializing. So we can just grab its name and write that to an output stream. And then here's the recursive call. This is the recursive algorithm on class structure. So we have a reflection of member. We're going to splice an access, it's a splice access expression. We're going to splice an expression that accesses that member, even if it's private. And then we're going to recursively call right on that particular data type. And like this is where the access to private data members things happen, is required. If we can't write access to private data members, this recursive walk does not work. And I would have to provide some code somewhere to serialize my player class. Right? And then the rest of this is just adding commas and stuff like that. But that's the entirety of what it takes to serialize a basic data type. This is kind of a summarized view of what that function actually looks like when you specialize this for health. So I took out all the counting stuff in the commas, but the expansion statement for each one prints out the name of the data member, and then we'll recursively call right on an access of that particular data member. And this would look the same if we did it for player, except we'd write object.mname and object.mhealth and object.mmagic, and we'd have 3 of them instead of 2. So, all right, I'm going to talk briefly about deserialization because it's going to turn out that these algorithms are basically the same. Like deserialization is the inverse of serialization. So we kind of expect these algorithms to be really closely related. If they're not closely related, if they're not structurally similar in some way, then we're probably solving something wrong. I will say though that deserializing is like an order of magnitude harder than writing data out, because you effectively have to write a parser for these things. And there's some really good questions about how you actually create the objects that you're deserializing, although I ended up punting on that particular problem. So I would say that if you want to look at the implementation in the structural algorithms repository linked at the beginning of this, there is an implementation there. It is a parser written on top of IO streams. It is not intended to be fast. Do not use it in production. It's probably wrong, but it works for the example, so it's good enough. But anyways, the structure of the solution is really kind of the same as what we had before for serialization. So I'm just going to show you what the deserialization code looks like for this, or for the corresponding read class function. So it's not particularly difficult. We match the enclosing brace, and then we just have a while loop that consumes key value pairs, looking for a closing brace and a comment at the end. So the first thing inside of each loop is first you get the key out of it by scanning the string, which just returns a string. You expect the colon, and then you call this function read member, which is going to recursively try to initialize each member variable of object given its particular key. Right? And that function is this. It's also not particularly complicated. And if you guys remember what, sorry, guys, it's an Ohioism, I think. If you remember what the toString function looked like for enums, this is almost exactly the same thing, except instead of searching for a value, we're searching of an enumerator, we're searching for a member with a particular name, right? So the structure is almost the same. Here we're iterating over a reflection of the data members of the class. So this will give us a constexpr range of members. We're going to have, it's another expansion statement. So we're going to expand. So each member is going to be a reflection of each data member. And again, the recursive call is just splicing this member access expression so that it can be assigned from whatever text has been read from the input. And that's it. Like that's the entirety of deserialization. Okay, so all of this is defined in terms of this notion of a basic data type, serialization, deserialization. I like this idea of a basic data type. There's probably a better name for it. I couldn't think of one. I'm sure that I will hear from people over email and Discord or other sources or Reddit what better or more appropriate names are for this concept. That's fine. But I like basic data type for now. So what exactly is it? Not an easy question to ask or answer, actually. Basically it's a class representing entities in an application domain. It's not going to be a complex data structure, like it's not string, which turns out to be kind of complicated with small string optimizations these days. It's not like vector, maybe not even like linked list, which is not particularly complicated, but those data structures represent values and encode a representation of values in a way that's different than kind of application domain entities would. It's usually not a model of library-specific concepts like range or predicate. A predicate can be a class, but it's not really a basic data type. It's not a random number generator. It's not a graph. The reason it's not usually one of those things is that we typically have rules for how to operate on those. If we know about them, we have specialized rules for how to operate on them. It's not variant-like. It's probably not tuple-like either, but maybe it is tuple-like. I don't know. So it doesn't have any union data members. I know that most implementations of standard variant use character buffers instead of recursively composed unions these days, but it probably doesn't have those either. It's not closure-like. Like it doesn't have reference data members. I tend to think of classes with reference data members as being closure-like, kind of like a closure for a lambda expression that captures by reference is sort of closed over a set of local variables. At least that's kind of the way that I think about it. But it may have private and protected data members, like my player class has private and protected or has private data members. It might have base classes. It might be polymorphic. It might have virtual base classes. Those things don't necessarily prevent a class from being characterized as a basic data type. They're just sort of properties of the class that affect behavior of algorithms in certain contexts, like whether you can memcopy the object or not, right? But they're not essential to the characterization of what a basic data type is, I think. Right? So I think the question is, can we define a concept for this? And the answer is yes, we can try. And this is my attempt at doing that. So a basic data type is a class, because if it's not a class, we already have concepts to describe it, like integral or floating point or pointer. So it is a class, and it doesn't have any what I'm going to call irregular subobjects. And so, well, what is an irregular subobject? So I can kind of give this little inductive definition and just say, a class is irregular if any of its non-static data members have reference or union type, so it's automatically like if it's closure, it's like a closure, or if it's like a variant, it's not going to be regular. We can draw a line there. If any non-static, if the class has a data member that is itself irregular, the class is also regular. If it has a direct or virtual base that's irregular, it's going to be irregular, right? So this is a basic inductive definition on the irregularity of the class. And we can actually implement this using the metaprogramming library, right? It's a really straightforward walk over the data members of your class and your bases and your virtual bases, looking for this one particular property. So, I'm actually going to cheat my definition of this, because that pattern of recursively walking over local data, like your data members plus your basis data members plus your virtual basis data members, we can just write a meta function that grabs all of those in one shot and flattens that entire view. And so that's basically what we've done with the subobjects of. I don't know if we can see this. Let's see here. This meta function right here will just give me a flattened view of everything inside of the class. And so then we can just write a function that walks over the members of the class and finds the type of each member. And then if it happens to be a reference or happens to be a union, then we'll just return false. Otherwise, we'll return true that it has no irregular members. And so that's the entirety of this particular concept. So just a couple of things to, already underlined that. So just a couple of things to point out about this definition. It's not complicated. There's no templates here. There's no constexpr. There's no expansion statements. This is just a regular function with a regular for loop that happens to operate over types as variables using plain C++. There is one reflection in here, but it just sort of falls out of the implementation, which is fine. I tried to write a version of this that was not a template and that you would just pass, where's that concept? You would just pass the reflection of T directly into no irregular subobjects. But I think there was a compiler error that prevented me from doing that for some reason. And so I ended up making this a template. But again, metaprogramming, this is just a regular function that operates on types as if they were normal values, because that's what we want for metaprogramming. Okay, so how much time do I have left? A fair amount. So I'm going to talk about hashing as my second example. I'm going to talk about it really quickly. Specifically, I want to talk about Howard Hannon's 2014 proposal, types on no hash, because I like this proposal a lot. It's great. It appeals to the generic programmer in me. And the fact that it's related to serialization is just kind of a happy coincidence. Basically, hash codes are accumulated by appending bits into a hash code, into something that then permutes those bits into a hash code that satisfies various mathematical properties. It's fantastic. So one of the pillars of Howard's proposal is this overload set called hash append that we can use concepts to constrain very nicely and select out the kind of behaviors for our standard fundamental types, like whether the integers, floating point values, or pointers, or bools, or something, or whatever else, right? But I didn't want to implement this as an overload set. I actually wanted to think about it a little differently. So I ended up rewriting the entire example as a customization point object, and that slide title should say customization point objects, not points. So if you're not familiar with the term customization point object, this came out of Eric Niebler's work on the ranges library, basically as a mechanism of controlling argument dependent lookup. So when you call, for example, when you call standard begin, we always want to start a range with call to standard begin. We don't want to have to write using standard colon begin and then begin. There shouldn't be a little two-step dance that you do to do this. The problem is that when you call into that thing, you actually end up with this problem that you have to effectively manage an overload set that can include member special customizations by member functions or customizations through argument dependent lookup. So these customization point objects are a way to encapsulate in that logic in a way that makes them sort of invisible to users. Hash append makes a great customization point object. So we only ever want to call like lock3 hash append for these things. And we'll just have that automatically support built-in types, standard concepts like range and whatever, containers, destructurable types it's going to turn out. But we also want to support customization through non-lock3 classes, like things outside of our library. And then of course, again, back to basic data types, if I have a class like player or health or magic, like it should just work. I don't want to have to write any extra code to hash those things. Now I can kind of like elide a lot of this talk because it turns out the design for this particular customization point object looks a lot like our JSON reader and writer. Writer anyways. it's going to have some of the same properties and solve some of the same problems. Right. So this is kind of what the initialization or the initial version of our customization point object looks like. It's just a class. It has some overloaded member functions. These are exactly the functions you saw before, just spelled operator parens and not hash append, but they do the same thing. And then we declare a constant expression variable, a constexpr variable type hash append at the bottom. And yes, this is legal C++. I would have written this differently, but I wanted it to appear on the slide, so you get the really weird spelling of constexpr variable declarations here. So if we want to manage classes, like everything else, we have to think about a little bit more carefully, right? So our other hashable types can be ranges, which are classes, usually classes. They can also be arrays. We have tuples. We have classes that have a member hash append. We have classes that have hash append that might be friend function definitions, or they might be declared in the class's namespace, but they're not in lock 3. And then we have these basic data types. And again, this is the exact same problem we had before with these kinds of things, is that we have a set of concepts that are completely unrelated to each other. And so we can't design a concept hierarchy where overload resolution is going to solve these problems. It has to be done with preference, or sort of preferential dispatch. And if you actually go and look at customization point implementations, customization point object implementations in GCC, for example, or libstandard C++, they actually do exactly this. You know, if you have a member, if your member is hashable, then go call that member function. If we can find this function through ADL, then go do that thing. If it's arranged, then do that thing. And so this is effectively what our overload for sort of everything else is going to end up looking like. Right. Oh, and by the way, destructurable is the case where we have things like standard tuple and a class that has all public data members, for example. Right. We tend to prefer to serialize things that way as opposed to basic data types, just because that'll pick up an interesting set of classes. They overlap with data types, but I prefer to do it through this mechanism than any other, for various reasons. Okay, so I was going to show some of these other examples, but I think there's probably not enough time. This is append data type. This is the actual code that hashes into or hashes a basic data type into a hash code, and it should look familiar at this point. It's just a recursive walk over the structure of the class again. We're reflecting over the subobjects of T, and we're gonna operate on the constexpr range of the subobject T. There's an expansion statement again. We're binding each subobject to a constant expression, and then at the end of the day, we splice that back into member access expression. And so we never actually have to, for a lot of classes, we would never have to write a single line of code to get the benefit of hashing for this particular facility. I did want to point this out because we are talking about generic programming and reflection. In the context of generic programming, we can also do better because you can always do better in C++. So it turns out that if a type is uniquely represented, meaning that sort of broadly, meaning that if every permutation of bits in its representation corresponds to a distinct value, more or less. So like 2's complement signed integer is uniquely represented. Every bit contributes to the value, and every distinct permutation of bits is a distinct value. It's signed to 2's complement signed integers. Floating point values are not, because you have -0 and 0, which have different bit patterns but correspond to the same value. For example, classes with padding bits are not uniquely represented. But there's a type trait called has unique object representations in the standard library. We can actually write this in using metaprogramming. It's just a recursive walk over the class structure. Today, this is implemented by a compiler intrinsic, specifically because a library implementation would need access to private data members to define it, which we actually get with reflection, static reflection. We could write this. I didn't because I ran out of time, so we'll just have to rely on this thing. So it turns out that basic data types can be uniquely represented, like the ratio class, if you remember from way back, just a pair of ints, that is a uniquely represented data type. And because it's uniquely represented, we can just hash it as its sequence of bytes. So we can just this is exactly the same as hashing an array of integers or just an integer by itself. We can just directly access the underlying representation of the object and hash them in a simple and efficient for loop, possibly unrolled. and with whatever optimizations apply in that context. So we can get a lot more efficient hashing with simple concept-based overloads and static reflection to prevent us from having to write a whole bunch of code to make this just work. Okay, so just a few more examples, a couple of things I want to talk about that are not related to the last examples, just because we can do these things with reflection. I haven't found great use cases for them yet, but they're things that we can do. So, for example, have you ever wanted to pass a function template as a, or function template as a template parameter, which I guarantee you that this is not valid C++ today, but that would be a function template parameter. Or maybe you've wanted to parameterize a template over a namespace. Like that seems like it might be something that you could do some really interesting things with, perchance, maybe, I don't know. There's a proposal for the latter one. I don't think there's a proposal for function template parameters or variable template parameters. I think I've actually run into that case once or twice. Or concept template parameters, which would be really interesting, which I should put on the slide, but I have not. So it turns out we can't do that with C++ without a lot of language work and a lot of language rules, but we can just do that with reflection. Like we just got that for free. We can't really specify the signature of function templates, so it's a little bit weaker than actually supporting function template parameters out of the box, but we can still do it, right? So we can, instead of passing the template by itself, we'll just pass its reflection. And when we want to use it, we just splice its reflection back into the program, and then we can call it like a regular function, and that is a function template parameter. Although, again, we can't specify the signature of the thing very easily, but maybe we can in the future. Namespace is the same thing, right? We just pass it by its reflection. We'll go ahead and write a little concept here to make sure that it's a requirement to make sure that it's actually namespace. And then when we use it, we can just splice it in as part of a nested name specifier. And now you can write a generic function whose behavior depends on a namespace defined elsewhere. I don't know whether that's useful, but it can be done. Although I have to point out that instantiating templates with namespaces is weird, because if you reopen the namespace after you've instantiated something, like what happens? There's some interesting questions that fall out of that. So, you know, how many people have ever actually wanted a type trait like is specialization of, where I can ask if some class is a specialization of a particular template? I know I've wanted this a few times, and I'm pretty sure I've gotten an email asking me how to write this. And there's no way to write it today. There's actually a proposal that would support this. And effectively what you need is a universal template parameter, something that can represent either a type or a value or a template declaration, right? So I mean, if we try to write this, like here's my best stab at this today. I can write is specialization of with a variadic template parameter. Unfortunately, if I try to specialize that with or instantiate that with array, I'm going to get an error because I can't match array to a variadic template a template with a sequence of type parameters, right? Because array takes an integer as its second template argument. So this doesn't work on a fundamental level. But you know, we can make that work with reflection, with metaprogramming. It's not hard. So instead of passing arrays, we can just pass reflections around. You know, if it's not a template, it's false. If it's not a specialization, it's false. And then the actual definition of this thing is really straightforward. We can just ask for the template of the specialization. All specializations are produced by a template. And then just compare that equality comparison to the reflection of the template. And that'll give me true or false. Right? So we can actually ask, you know, standard cout is specialization of the reflection of an array and then reflection of int. And that should print false. Or you know, we can do more complicated things, but we can actually write this type trait with reflection, or this query. And of course, you want that as a concept because what you really want to do is write a concept or a template that's guarded on the fact that whatever type you provide is actually a specialization of some template. And now that we kind of broadly know what category of operations are available inside of that template. So we don't have to define a concept for this thing, or rather the concept is just all types that are specializations of this template. And that's how we can do that. So I am now at my conclusions. Just an observation on the structure of a lot of the examples here. all of the examples, with the exception of the last two cases with namespace template parameters and its specialization, a lot of these examples kind of have this sort of pattern, right? We have normal code that's just calling into a typical template facility, just a generic library. And all of the reflective stuff happens in the back end of that template, whether we're using reflection as just constexpr evaluation to provide template type traits or to help define concepts, or to generate reflections of new types or values or whatever. Like these templates are just calling into some facilities that are actually doing this metaprogramming. It's very rare that we actually directly move from normal code into reflection. They're almost always run through an intermediate of a template. And then the template gets all that information back and it splices it back into its content as it's being instantiated. And then that generated code is handed back to the normal code for runtime computation. And I think this is going to be a fairly stable architecture for the way that we're going to use metaprogramming in the future too. I think that most of our uses of metaprogramming will be hidden behind some layer where you're not directly working with reflection or splices. Rather, that stuff sort of builds into the facilities that we've already built generically. So my kind of view of this so far that I've taken, or the view that I've taken from this, is that status, great, nice typo. Static reflection really improves generic libraries. That's what I want to use it for. At least just static reflection. We can write less boilerplate. I think writing no boilerplate is less than some. So that's a big win for me. Like I don't have to do anything to serialize to JSON or to write hash functions anymore, unless I'm doing something interesting. We get better opportunities for customization, although that largely falls out of the way we use concepts and overload resolution and customization point objects and other design patterns. We get more optimization opportunities. I think we get easier optimization opportunities, or they're easier to find, although that has as much to do with concepts again as reflection. And we definitely end up with fewer language features. We don't have to keep dipping into the compiler to implement things like has unique object representations, or is basic data type, or is standard layout, for example. These can all be library features in the future. And there's probably a whole bunch of things that I'm missing. Like I haven't been that creative with my use of reflection to do crazy things. So there's probably a lot of things that people will find that it can do that I haven't even remotely thought of. And so I'm kind of looking forward to see what people end up doing with this, and seeing how it moves forward. So thank you for listening to me ramble for, how long was that? An hour and 20 minutes. Wow, a little longer than I thought. But again, thanks for your comments or questions. Okay, so I'm just going to go from the top down, read questions here. I'm new to template metaprogramming or metaprogramming in C++, but self-studying for later. How does this proposal differ from circle-lang at a non-syntactic level? I am going to tell you that I am not an expert on circle, and so any comparisons that I make would be likely bad, I think, for lack of a better term. I used to have a good answer for this, but I think I've forgotten in the interleaving year, just because I've been more focused on making this work and less focused on what Circle is doing. I think if you want a good answer to that question, then your self-study will also require your own comparison for that. Sorry. Are there build time implications? Yes, there are build time implications. It'll be interesting to see how this kind of pans out, because there are a number of features or factors that are going to go into this. So template instantiation is already a build time consideration, right? Instantiating class templates is already slow. What we're doing with this approach to metaprogramming, making it all constant expression evaluated, is moving away from templates, basically replacing template instantiation as the evaluation mechanism and replacing it with constant expression evaluation, which is basically just changing the kind of compile time overhead that we have. I think some early experiments show that, like, an instantiation-based algorithm and a constexpr-based algorithm, we get a clear win for constant expression-based evaluation. It's good. The downside is that the more metaprogramming you have, the slower your build time is going to get, which is unfortunate, but that's just a fact of life. We're like literally just forcing the compiler to do more work. If somehow our compile times got faster while the compiler did more work, I would be surprised. That seems like it shouldn't happen. The thing that might actually provide some mitigation to this is modules. The idea is that maybe we can kind of cache or memoize certain computations in a module that are exported from a module and import them into clients in a way that we can avoid redundant computation. Although I do have to point out that one of the reasons, like if I go back to this slide here, one of the reasons that I like this particular model is that all code that calls to a template, like templates are already memoized. And so even in modules, if you export a template, you're not going to rerun any of the reflection, like any of the constexpr code behind that. Once a template is specialized, any name that refers to that template is just going to get the same thing. It's just a hash table lookup in the internals of the compiler. So if you sort of skip that template layer, you're going to run into recalculating a whole bunch of things at compile time, and it might make your program slower. If you actually do have a template that memoizes results as part of a specialization, you might mitigate some of that cost in large or metaprogramming heavy translation units. Let's see, question, can we expect this in 26? I hope so. We'd have hoped to have it by 23, but I think the pandemic kind of hurt our ability to make progress on this. So we might be talking about a new reflection TS. I hope we can get this in 26. I hope we can get it in, it's not going to happen for 23. I think that's just out the window for now. But so I hope we can get into 26, sorry. Okay, so what kind of reflection capabilities will there be for attributes? Excellent, excellent capabilities for attributes. I don't know the answer to that. So attributes are kind of weird. I actually wanted to have, before this talk, an implementation of meta functions that access attributes on declarations. But we ended up running into an implementation issue in Clang that the attributes that you would want to add to something tend to not be supported by the compiler. And so anything that you would write as an attribute on a class, for example, ends up getting an automatic warning that the attribute doesn't, like there's no interpretation of the attribute, which is kind of unfortunate. One of the other ideas that kind of came out in P2237 was this notion of a stereotype, which was sort of a replacement for a meta class. If you've seen Herb's talk on meta classes, it was an annotational device that just gave, like, it unified some of these ideas into sort of a single umbrella. Meta classes being part of that. I've been thinking about trying to use stereotypes, however they're going to evolve, as a way of plumbing user-defined attributes to the system in a way that is not that doesn't conflict with what we normally think of as attributes. And the more important part of that about these stereotypes is that the code inside of a stereotype, which was just two angle brackets, like if you've seen a stereotype in UML, it's the guillemets or the two angle brackets. That whatever you put inside of those has to be an expression, or has to be something that's parsable, and that's not true of attributes. There's a grammar for attributes, but it's not an expression that you can actually execute and evaluate. And I think what I'd like to do is actually have that syntax be used for reflecting user-defined attributes and values, or associating compile time data with declarations and definitions, if that makes sense. Are there C++20 compatible libraries using macros that implements this part of the specification? I believe so. I know there's somebody pointed me at a Boost library that Peter Dymov wrote that's being reviewed. It's not a Boost library yet, it's being reviewed for Boost, I think started soon. And I know that like the two first examples that he had were toString for enums and JSON serialization. So yes, there probably are C++. Well, that library is actually C++17. I don't know about C++20. I haven't seen one yet. So question, what is the difference between *t and meta type of *t? Well, it depends what T reflects. If T reflects a type, then, if T is a type, then the reflection of type is a type. If T is a type, then meta : type of is ill-formed. It's not necessarily ill-formed, but it's an invalid reflection because you can't get the type of the type. If T were anything other than a type, like a variable or a function, then the reflection of T would give you a handle to that declaration, for example, and then meta : type of the reflection of T would give you a reflection of the type of that declaration, if that makes sense. I hope that makes sense. Is reflection powerful enough that it could reflect on all the declarations in a namespace and serialize those declarations to a valid C++ header? Presumably, yes. The one thing, so we can already do that today with reflection, just iterate over the members in a namespace. I think we can. There are some weird library issues with traversing members of a namespace, like what happens if you reopen it. But the one thing we can't do today is to actually like dump those declarations to a separate header file. We can't extract them. That's kind of those other orthogonal requirements of actually having external data that we could write to as we run a metaprogram. All right. So, question: a small point on nomenclature. It might be useful if the name for basic data type hinted at clearly differences from plain old data. See, I knew it. People are going to have opinions about basic data type. Yes, I expect that name will be bike shedded considerably, but I think there's a concept there. I just don't know what the name is. I don't know what properties the name should have or what it should convey. But everybody will have an opinion on this one. I just needed to get a name out so I could write these slides, and basic data type was it. Slide 111, is there a difference between constraining to a specialization centered array and specifying an array of T in a template type? No, there's not. If you write your specialization, if you're in a context where you can write a specialization, where you can write a partial specialization over the syntax, then you can do that. But that's not always the case, right? So you can't partially specialize function templates. And there are definitely cases where I have like an explicit template argument that I always want to be an array, but I don't have a mechanism to say always match these particular this subset of types. I'd have to run that through a class template partial specialization instead, which kind of defeats the purpose of what I was trying to do. So the answer is both yes and no. Can I reflect on the type of a lambda? Yes, you can reflect on the type of a lambda. I don't know what you can do with it, but yes, you can. And lastly, can I reflect on a non-constant expression? Absolutely, you can. So one of the features down the roads that we talked about in P2237, which is an incredibly underdeveloped part of the paper, is this idea of macros. And there's kind of this idea that, like, in the future, what we'd really like to do is sort of introduce a new parameter passing mechanism for C++, which is passed by reflection. So if you think about a normal function, like, instead of taking an argument by value or by reference, you can actually take an entire expression as an argument, and then you can kind of inject or analyze, inject, and synthesize code related to that particular expression. But the expression itself, it's not a constant expression. It just happens to be an expression that was written in a context where a function was called. And that turns out to be exceptionally powerful. In fact, I think it's pretty close to what Rust does with their macros, except that our macros are fully typed. So you actually know the semantic properties of the expression that you get as an argument. And you can ask for its type, and you can ask for its contents and things like that. So I hope that answered your question. Okay. So that's it. If you guys have any other questions, I'll be around. I see that a hand is raised. How do I see this? Attendees. So now that a hand is raised, I'm not sure what to do. What's the policy here? Do I allow to talk? Sure. Yes.
Hello. I was just I've been fiddling with this since I saw it this morning at another talk. And I'm getting a thing of reflection reflects an expression which is not constexpr. So is the branch not yet fully up to speed with that kind of stuff, with the macro stuff, or is that? Or am I doing something
reflects,
drastically wrong?
reflection reflects an expression that is not constant expression. Yeah, I patched that. I patched that in a branch on Saturday.
Okay,
it may not be in the current version.
Okay, so it's a compiler error and not a limitation of the.
Yeah.
Sense.
There's still some really interesting issues with reflecting non-dependent expressions and especially splicing them. But my belief is that this should be able to work. And if it didn't, I would not be able to get a version of macros that I wanted.
Yeah, well, I'm trying to do something like macros because that sounds interesting.
It does.
Awesome.
I'm kind of excited for that feature.
Yeah.
Yeah, like one of the things I think that we get from that is the ability to pass overload sets as function arguments, because you're just passing an expression and deferring resolution of it. So you could do things like call sort and then pass just the identifier operator less.
That's cool.
That would be cool. And there are proposals for that too, but I don't think any of them get as elegant as being able to pass this by reflection.
Nice.
Okay. Any other questions? No other hands? All right. Yes. Does this allow us to replace uses of decal type? Yes, it does. You don't need decal type anymore because you can have an expression. You just take the reflection of it, and you get whatever its type is. In fact, David and I were talking about this, and we actually ended up deciding. I think we ended up deciding that we would actually get rid of the that weird little property that decal type has, that it will give you the declared type of a variable instead of the actual type of the expression. So it's the semantics will be a little bit different. You'll always get the type of the expression unless you explicitly ask for the declared type of a variable. So we thought that would be a little bit more consistent than having that weird little wrinkle for decal type. All right. Nothing else? Okay. Well, thanks for coming to my talk. I'm glad I could entertain you for 90 minutes or so. But okay, I'm done.